So, today in this chapter, we are going to start with conservation of momentum. But before that, let's have a recap of all the things that we have done in laws of motion. We have basically studied the first law. It was based upon inertia, the property that every object in the universe has. That is, it needs a force to stop moving or it needs a force to start moving. This is the basic property, or you can say a characteristics of all the body which has mass, inertia. Now, in the second law, what we studied was the rate of change of momentum. That is, if this is my change in momentum with respect to time, that is known as your rate of change. This is directly proportional to the force applied. This was what we studied with the second law. Now coming to third law, what we have studied was every action has a equal and opposite reaction. If this is F1 and F2 and these are two bodies, so if this reacts with this with a force F1, then the body also puts a force F2. And according to this particular law, what we find is that F1 is equal to F2. So this was all what we studied regarding the three laws of motion of Newton. Now there is another important aspect, or what you can consider, is that it relates to the second law of motion. That is, the rate of change of momentum is force. Now from that we can further derive, say for example, you have a body of mass m. Now this is moving with a velocity v. Now after some time it changes from v to v plus del v. That is, the momentum changes from v mv to m into v plus del v. This is the change in momentum with respect to the previous value, that is mv. You can give a vector sign over here. So this value changes. Now the time interval at which this changes is del t, or you can say that t was the initial time and t plus del t was your final time. Now if you look over here, what you see is that rate of change, that is force, is directly proportional to rate of change of p with respect to del t. Now this implies m del v upon del t. This is the rate of change of v with respect to time t. Now if you take limit where del tends to 0, then del v upon del t, that is the small change. Now I often find in students that they are not able to relate with the book. Say suppose you have been given a definition in the book, that is in your NCERT. Now you get confused while reading the book. You will see this particular expression. So the explanation of this particular expression is that, say suppose you are moving with a speed v. Now there is a small change. In your speed, a very minute change in your speed, say del v, for a time interval, that is a small time interval, del t. Now this del tends to 0. Now what does this mean? Tends to 0 means we are taking a very small interval. This means that, say suppose we are making a graph. This is your y-axis and this is your x-axis. If you are plotting over here the time, this is time, and if you are plotting a velocity v, and if you're plotting a velocity v, say this is velocity v. Now velocity is increasing with respect to time. This particular velocity is increasing with respect to time. So when you talk about del v upon del t, what we are doing is actually we are taking a very small quantity that is velocity, this part and this part, this particular part a very small quantity, and this particular part a very small quantity. So what happens is we can form a triangle, a right angle triangle. So this is very so this is a minute part, and this too is also a very minute part that we can easily neglect. So that is why we have used the notion del v, where limit del tends to 0. Now if limit del tends to 0, this particular expression becomes dv upon dt, where this is a minute change and this is also a minute change. Now, as we know, we have discussed in our previous chapters, dv upon dt is nothing but your acceleration. So this is proportional to acceleration. Now, f is proportional to acceleration, and f is equal to ma from this particular equation. M is your proportionality constant. So in this way we can prove that the second law tells about force equals to mass into acceleration. Now, as I've discussed in a previous class, the second law does not talk about m equals to f, but it implies that force equals to mass into acceleration. The second law is not f equals to ma. So this was what we discussed in our previous and today's class. Now, after a brief recap, let's come to one of the most important part of motion, that is conservation of momentum. Now, when we talk about conservation of momentum, we are talking about this conservation. We are conserving the momentum. Now, we know P is equal to mv. That is, if a body of mass m is traveling with a velocity v in a particular direction, then we say that the momentum of that particular object is m into v. That is, it has a momentum of m into v. Now, let's give you some examples. In your book, it is given that a ball has been attached to a string where a person is holding the string and he's rotating the ball. So how is force being applied to this particular ball if it's moving in a constant velocity? If the ball is moving in a constant velocity, how are we applying force, or how is the momentum changing? The answer is, say suppose you have a ball. You can do this experiment in your home. If you have a ball and you tie this to your string and you keep on rotating, what you will find is that you feel a pressure in your hand. And that pressure is because even the ball is rotating at constant speed, but every time its direction is changing. And that is the reason, in order to change the direction also, you need to apply force. So what we can say is that we are changing the momentum. Now, as I've mentioned in my previous class, that momentum can also be changed by changing the direction. If mv is the momentum in this particular direction, and if I change the direction to over here, then mv also changes. The previous momentum and the next momentum is different because momentum is a vector quantity. So this was the example that was given, and this is how we can understand. Now we will discuss this more in the chapter of rotational mechanics, but for now what you need to know is, if you change the direction, your momentum also changes, and if you're changing the momentum, you need to apply force, and this is a perfect example of momentum change with applied force. Now let's come to the point where we are talking about the conservation of momentum. Now this statement states that if you have an object m and it's traveling with a velocity v, so by conservation of momentum, the total momentum of this particular object, the total momentum of this particular object is always conserved. That is the overall momentum. The overall momentum is p equals to mv. This is about direction. Now you can see that the value p equals to mv, the value will always be conserved. Now let's take an example. This is a ball of mass m and it's traveling to strike the wall. It's traveling in a direction that is parallel to the x-axis to strike the wall. Now according to this law, according to the conservation of linear momentum law, what we see is that even after striking the wall, the ball moves back. That is, it's moving in the opposite direction, that is minus of v. If it's traveling with velocity v in this particular direction, then it's traveling the opposite direction after striking. So by conservation of momentum, what we know is that mv will always be equal to m minus v. That is the value will always be equal by conservation of momentum. Now this was what mathematically we have been told. Now let's understand this with a real life example. Now for this you have to keep in mind that this particular scenarios are ideal conditions. They are ideal in the sense that when the ball strikes the wall, they say that there is no loss of energy after striking the wall. That is, it's striking elastically. That is, it's striking elastically where E equals to 1. The coefficient of elasticity is equal to 1, where it is known as perfect elastic. That is, if an object strikes the wall or the elasticity which has the coefficient of 1, it will not lose any energy. It will straight away impart the exact same amount of energy that it has been struck with. And this is known as a perfect or ideal elastic. Okay, so that was an example that we can look into while understanding conservation of momentum. Now there are certain points which I said was there are certain points which we mentioned was that it should be elastic. So now you may ask me a question: what happens if the surface where it's striking is non-elastic? Say suppose this is the surface and the ball is striking at this particular point. What happens when this is non-elastic? When this is non-elastic, so will the conservation of momentum hold? The answer is conservation of momentum. Conservation will always hold true. Conservation will always hold true. Now the next question that comes is, why don't we see this conservation of momentum in nature? In nature, why don't we see conservation of linear momentum? If we strike a ball with greater speed, after striking, the speed reduces. the speed reduces, that is the momentum reduces. So why is this so? The answer is conservation of momentum always holds true. But what you see is when you throw a ball, there is air resistance. So in order to overcome the air resistance, you apply a certain force. You apply a certain force, and this force or this force that is generated, the resistance that is generated, reduces the speed. And the wall is not perfectly elastic, so it does not impart the same energy while returning the ball. So there is a loss of speed due to air resistance. There is a loss of speed due to inelastic. Now, sum up, if you sum up all the factors, that is resistance and the energy or the heat that has been produced, plus also the sound. When you strike a object, heat is produced, plus sound, plus the material which it's getting hit, that is the object where you are hitting the ball, also gets a bit changed. The perfect example is that, say suppose you have a wall and a ball, and you keep on hitting the wall every day with the ball, you will see that the shape of the wall is changing because it's not perfectly elastic. So if you factor in all the conditions, that is energy loss due to sound, energy loss due to heat and material, plus also the resistance, then if you sum up all the factors, you will see that this is equal to mb. All the all the factors, if you sum up, this will be equal to the initial momentum plus all the factors plus the new momentum, that is with the new speed that it's coming back. So in real life also conservation of momentum holds true, but we cannot observe this with our eyes because there are certain factors which we cannot comprehend. So what we can conclude is that conservation of momentum always holds true. Now let's come to the next topic, that is equilibrium of a particle. Now the equilibrium of a particle in mechanics refers to the situation when the net external force on the particle is zero. Now this was what was written in our book, but what does this actually mean? It was written net external force in a particle is zero. So the net external force in a particle is zero. Now this can also be related with your inertia. This is your inertia. This particular object, say of mass m, equilibrium of a particle, we can relate this with inertia. Now the question is how? The answer is a body, if the net force of a body is zero, the net external force of a body, if it's acting is zero, the body will either be in motion if the body was previously in motion, or the body will be in rest if the body was previously in rest. Now if F1 equals to minus F2, the meaning of this is that, you may have seen this expression. The meaning of this is, say suppose this is object of mass m and a force F has been applied. Now in order to neutralize this force, we will apply another force, but we have to be sure that we are applying in this particular direction, that is the net force on y and x axis should be zero. So this is in the direction of x axis, so f of x equals to f, and f of y is equal to 0. F of y is equal to 0 because there is no component of y in this particular force. The reason because it's straight away going towards x-axis. Now when we talk about the net force should be 0, if a force of F has been applied over here, in order to neutralize this, we need another force. And it should be equal and opposite. Now we are also using Newton's third law. And Newton's third law states that this should also be equal, that is the magnitude should be F, plus it should be equal and opposite. So the answer will be F resultant is equal to f of x minus f of x minus. Therefore, in two cases what we see is f of x is equal to minus of f of x that we are putting in, and this is the resultant and this is the actual. Now if we put this in your left hand side, this is your left hand side and this is your right hand side. So if I take this into my left hand side, f actual plus f resultant should always be equal to 0. This should always be equal to 0, and this is what equilibrium of forces mean. Equilibrium of forces mean that net force that has been applied in a object should always be equal to 0.